Good. Yeah. So this is the noise model. Okay. So that our observations are are concatenations, are superposition of a clear signal that should lie in a low dimensional subspace plus some noise, and the noise is Gaussian distributed. That is the idea behind that. And we say, well, if this is the case, then we can look at the maximum likelihood interpretation and how to explain, or how to find this low dimensional subspace that best explains our observations given this model. And so that's where we want to go. So we consider x to be the input variable, and we say that x is L plus n, where realizations of L are assumed to lie in a k-dimensional linear subspace, and n is assumed to be Gaussian distributed. And of course, components are here independently distributed. And principal component analysis in that setting could be interpreted as finding the subspace from the independent realizations of x. Right? So if we look at the maximum likelihood approach, and we say that our noise Ni is, or the jth component of Ni is distributed here as N01, we know that the probability density function, probability of xi, or let's say Ni here, Nij is yeah, I mean we know the Gauss density function. I'm not so much interested into the constants. So there is a constant here. There is E. There is minus. There is another constant there. C1, C2, and we have Ni squared, right? Ryan, you have a look at that and see whether it's correct or not, right?
It's right. It's correct.
That should be correct.
Mm-hmm.
So this is what you observe if you have like one-dimensional Gaussian noise. And so what you do is so the probability of the observations, probability of observations x1, xn in RP given the model are, we have the probability of xi given the model here is so we have this product of I is 1 to n, and we have the product of j is 1 to p, because we're looking at each individual component. And we have the C1 times e to the minus C2. And here we have xij minus nij squared, sorry, lij squared. Right, because the difference between the observation and data that lies in low dimensional subspace is exactly this Gaussian noise. This is our model assumption here. So we have minus logarithm here of this xi given our model is something like, there is a constant. It's not the same constant. It's C1 tilde plus sum of I and j. Sorry, I and j, and here this is C2 times xij minus lij squared, right? Yeah, should be so. And if we write that in matrix notation, this is the same then C1 tilde plus C2 times, and this here is the norm. This is x minus L, and this is the Frobenius norm squared. Right? So that leads us. So if we want to find the best parameters that explain our observations, we have to minimize. So we want to maximize the probability or minimize the negative log likelihood. So this leads us to the approach. Leads us to the minimization problem. To minimize here, all AI lie in a low-dimensional subspace x minus L squared. And all Li lie in a low-dimensional subspace is equivalent of requiring that this matrix L has a rank of dimension k, right? A low rank, low-dimensional subspace. We have to like fix this low dimension. Low dimension here is too fuzzy, so we go to this approach here. Sorry. So this is a minimization problem.
So Martin,
yeah.
We have some question related to the previous slide,
yeah.
where the students are asking why we are letting xi go from 1 to n for every probability of xi given model. So if we go to the last slide.
Yeah. This slide here?
Yes.
Yes. So I mean, we have the question was why we go from.
So here, yes. So the question is why we are going from 1 to n, I is equal to 1 to n for every xi given model. So I guess here we wanted to have a probability of all the observations given model, not the observation xi.
Yes, exactly. Right. I mean, this is sorry, probability xi. I is 1 to n.
Yes.
This is probably missing here.
Yeah.
We have a bunch of observations. We have n observations, and we would like to find the model parameters that best suit all the observations that we have.
Yes.
But if we would only have one observation, it would be a trivial task, because only one observation giving this model lies the likelihood is that this observation is in a one-dimensional subspace, and then there is nothing to do.
Yeah.
So is that?
Yes, that's okay. That's clear now.
Good. So, okay, good. And that leads us to the minimization problem. We have to fix this K. This makes it clearer. Right. So we have to solve the minimization problem. Minimize this form given that the Li are an element of a k-dimensional subspace, and k is much smaller than p. That's the idea. And Li being in some k-dimensional subspace is equivalent of asking that the rank of L is smaller or equal to K. And that's just the definition of this, of the rank, actually. Okay, so yes, so we want to solve the minimization problem. So this is equivalent. This is equivalent to solving the problem minimize the rank of L smaller or equal to K, norm X minus L F squared. And this problem is also known as the best rank K approximation of the matrix X. Okay, so this maximum likelihood approach brings us to this optimization problem. And we have this theorem here that gives us a solution to that problem. And the solution is given by the singular value decomposition of X. Right? So that means if we have a singular value decomposition of X, then we can construct the best rank K approximation L by taking the first K singular values and the first K singular vectors of X exactly in that form. And this minimizes exactly this optimization problem. I haven't written that down again. This minimizes the problem here. Minimize rank L equal to K X minus Frobenius norm squared. Yeah. So let's have a look at that. Right. So again, I mean, how do we construct it? I mean, it's written here, but it's can also be visualized quite well. We have, if this X is given by the U and our diagonal sigma and our V transpose here, then our L is given by this. You have the first K columns of U, you have the first K entries of sigma, and you have the first K rows of V transpose. right? And this is said to be the best rank K approximation. Okay. Good. The dimension is K. Yes, this is K, K, K. And the dimension of L, of course, if you, I mean, L has the same size as X, right? This is a matrix, of course, in R. P times N. To make that clear. Good. Now let's have a look at that. Why is that true? So we say that, so the proof of that is, and we had the rank of L smaller or equal to K if and only if the columns of L lie in a one-dimensional, in a k-dimensional subspace. In a k-dimensional subspace. And then we we have this norm of x minus L. And then we observe the following. We have the the norm here of xi minus Li. If we look at I'm sorry. If we look at that, the squared norm here. Right, so I mean, if this is the subspace L, and this is xi, and we have here this here is Li in some subspace. We have that xi minus Li is always greater or equal to xi minus the projection onto that subspace L of xi squared, right? For all Li lying in that subspace, right? So that means that also the sum of over I of xi minus Li squared is greater or equal to the sum of I xi minus p norm squared, right? That's what follows here. Right. Typically, I'm missing the eye contact and some nodding in the audience, but I hope that this is. Yeah, I'm going to share these notes. Yeah. Right. So this means that the minimum for Li lie in some low-dimensional subspace L of the sum over I norm xi minus li squared is greater or equal to the minimum over dimension of L is K, and the projection onto one of these subspaces. Right? Ryan, you take care. Ryan, you're responsible that I'm not saying anything wrong, right?
Yeah,
You
I'm
take
also
care.
following it. Yeah.
Try to follow that. So this is one thing, but on the other side, some place is missing. On the other side, we have that the minimum here, dimension of L smaller or equal to K of this sum over I norm xi minus PL xi squared is, of course, also small, is greater or equal than the minimum of all Li in L of the sum of I. Right? I mean, why is that the case? Because the left-hand side, on the left-hand side, you have a subset of possible solutions compared to the right-hand side. Or on the right-hand side, you say, well, I want to minimize this function L. I want to minimize this this function, and taking into account all possible Li that lie in a low-dimensional subspace. Okay, and on the left-hand side, you have a particular realization of that. So of course, that can only be bigger, or otherwise said, the right-hand side can only be smaller than the left-hand side, because you allow more potential solutions, right? So in fact, what you have here is actually an equality sign. This is what you have here. So in fact, the minimum on the left-hand side and the minimum on the right-hand side are the same. And so we are done, because we have already solved the problem for the right-hand side, for the projections. And then we see that this is equivalent to this geometric approach that we had at the very beginning. Right?
Yeah.
So that says, and I'm getting a bit out of space here. That says that in fact the geometric approach solves the problem, and this is what we have already proven. So it's somehow the result of the theorem that we have already proven applies here. Okay. If that is okay, good. Questions or comments? Ryan, you want to say something? You're muted.
Yeah, I just wanted to add the same comment as we had from the last time, that the projection already maps X to a point that has minimum distance from the subspace. So inverse what you wrote the inequalities.
Yeah, I could not find the notes of the last week. I'm just reading the question. This is because last week somehow the my computer did not save the handwritten notes, but you can see the notes in the video, right? I think that you uploaded the video, right?
Yes.
You can find it there. Now, I mean, sharing the notes beforehand does not make so much sense because they are, yeah, I mean, they are empty a lot right before I upload them. On the other side, I mean that we have so we have on the one side we have seen that the minimum here is greater or equal than the minimum there, and on the other side we have seen that also the converse is true, so there must be an equality, right? I said that A is smaller or equal than B, and then I said that B is smaller or equal than A, and so B has to be the same than A. Right, and then I have reduced somehow something that we have already solved, namely within the geometric approach. By the way, I mean the proof is also written in the lecture notes. Also have a look at it. Okay, so that means we can continue, or should we have a break? What do you mean?
I guess we can have a break, maybe.
A small break?
Yep.
Okay. Then 3 minutes break or 4 minutes break, get some coffee, and then we are back and we look at autoencoders. Like, but that's something he's like created while I'm talking. Right? This is sort of the thing, and otherwise it's in the lecture notes and they should be easily readable. So try to follow. I mean, try to follow what I'm saying here. Yeah, and because there was another question. I mean, this is, if you're not aware of that, this is the same than x minus L Frobenius norm squared. Okay, I mean, this is exactly the definition of the Frobenius norm. And here X is a matrix. That's what I mean. Here X and L are the matrices. Yeah. So it's not very difficult. Good. So let's continue. So that was one thing, and the other thing, a very let's say modern interpretation of PCA is PCA as an autoencoder. And yeah,
Martin, just before we proceed, we have a question from Seeley. Says, sorry, I still have a question because I wonder, an example like L is a two-dimensional full-rank matrix, then does it lie in a k-dimensional subspace with k is greater than or equal to 2?
An example, L is a, well, I mean, so, okay, so I write the example here because here is still, I have some space here. So if L is a two-dimensional full rank matrix, two-dimensional full rank, like for example, L is 1, 0, 1, 1, 1, 2, I don't know, 1, 3, something like that. Then this matrix has rank L and all data points lie in a two-dimensional subspace. I can all plot them in R2, right? And the 0 is always in that subspace. So these data points here all lie in a two-dimensional subspace. Correct? What if k is greater or equal than 2? Well, then they lie in a three-dimensional subspace. Like this, for example.
But in that case, L will not be a two-dimensional full-rank matrix, so to say.
Exactly. In this case, it's a three-dimensional full-rank matrix.
Yeah.
k greater than 0, but the rank of L is smaller or equal than k. Yes, then I mean, then it's hard to draw a picture, right? But I can try, right? But it's I only have 3 dimensions for drawing, and even this is not the best thing to do. But for example, if L is of the form, if L is of this form, 1, 1, 1, 2, 2, 2, 3, 3, 3, then we all see that this has a rank of 1, right? And is that example? I mean, is that something that helps you? Because all data points now, if you are in R3, lie in this one-dimensional subspace where you have 1, 1, 1, 2, 2, 2, 3, 3, 3, and so on. And this here would be L would be one-dimensional because it has rank 1. Two-dimensional means that I have to draw a two-dimensional space where the data lies in. Yeah. And all coordinates of all 3-dimensional coordinates of these 2 points, if I plug them together into a matrix, this matrix will have rank 2.
Yeah.
Okay.
Yeah. But space
so,
is 3-dimensional.
Let me clean that because I need this slide. Autoencoders. Okay. Autoencoders, I mean, they are actually quite simple from the idea, but they lead to quite powerful results. And what an autoencoder is actually doing is it follows the idea that we have an input x, random variable x, in RP. Then we apply to it some kind of function which we want to find, some function f that let's say reduces this variable z, reduces to a variable z in Rk, and it says that k is smaller than p, and then we want to find another map G that goes back to Rp, and that says, well, the outcome here, call it x hat, and the outcome here should be approximately distributed the same way than x is distributed. This could be, or this is an interpretation of autoencoders, right? We want to find a map f that somehow squeezes our high-dimensional random variable into some smaller one. So we want to reduce the volume. And then we want to find a kind of reconstructing map G that tries to imitate our input variable x. This is the simple idea of an autoencoder. And the and f is called decoding function, and G is called encoding. No, the other way around. Ryan, right?
Yeah.
Yeah. Encoding function and decoding function. So right, I mean, the idea behind that is, or the picture behind that is, you have a signal x, and before you send it through through a channel, you want to like compress it or encode it, and then you put it into a function, and on the other side of the channel, your receiver has a decoding function G that someone wants to reconstruct the signal that is passed through the channel. Okay, that's a little bit the idea behind an autoencoder. And very often you see this picture here. You see the size here of your input signal X in RP, and you have your map F, and this goes into some smaller Z in RK, and then you want to reconstruct the G to some X head. Right. That is the idea of an autoencoder. And if we want to, or if we restrict F and G to be linear functions, then we have the same thing than PCA, right? So PCA can be interpreted as a kind of autoencoder function that is linear. Right. So in general, autoencoders. So this is something autoencoders. Encoders try to find best pair F of G for some reconstruction measure. And again, we arrive at our loss function. Okay, so so the concatenation here, we say that G, so F applied to Xi, and then applying the G again should be approximately the same than our input Xi. That's the idea. Okay, good. This is the picture again. And if we say that V and that F and G are linear functions, then we have the following. Then we have F, G, F, Xi is the same than V times Xi and then W, right? The V is here a matrix of that dimension, PK, and W is a matrix of this dimension, PK. So this is a matrix of dimension. This looks like this. And it is in R P times P, but it has a rank that is smaller or equal to K. Right. And this brings us to the approach here. If UK, and this is some of the result here, right? If UK is the first left singular vectors of the observation matrix X, then if V is chosen as UK transpose and W is chosen as UK, minimizes the reconstruction area of the linear autoencoder. Right, so we say if we want to minimize the norm of sum over I, norm of xi minus wxi squared. This is what we do if we want to measure the expectation of the squared difference of the input and the output. This is the linear autoencoder. UK transpose klein v and UK W solve the minimization problem. Minimize v W sum over I norm xi minus right? This is the result, and the proof here is rather simple because we have the rank of this matrix VW is smaller or equal to K, right? Because of the dimensions of V and W. V of W and V. And so that means that these vectors here all lie in a k-dimensional subspace. And so we have already seen in the proof beforehand that SVD of X solves the problem. And so it's equivalent to what we have already seen there. Good. So that's interesting because this approach really allows to generalize very well and to, of course, leading to better algorithms that reduce our dimension. Okay, so we have seen, so if we look at this autoencoder image, that with this V and W, we have reduced the dimension, and the decoding step reduces the dimension of the input variable to this, to this code, right, of the variable. And this code can be, and these codes are the principal components here. And we can reconstruct the signal also very easily. But in some cases, we say that, well, I mean, this is a good idea perhaps, but can we do better? And are there ways to generalize that? And an easy way of generalizing it is to say that I allow, instead of linear functions, I allow for nonlinear functions. And I go to nonlinear autoencoders, and I will just sketch that a little bit because it will lead us to our next big chapter. So these are the extensions to simple nonlinear autoencoders. It's just like, so we have successful here, very successful in applications. In applications is if we extend this idea to non-linear functions f and g. And nonlinear, of course, is a big field. And an easy way of extending nonlinear functions, of extending linear functions to nonlinear functions is that we just apply right after. So we have our x as an input vector, and we have the v here of x, and this here is a vector in, that's something in RK. And what we do now is to each of the columns of this x, right, let's write it like that. Let's illustrate it a little bit. And each of the entries that you have in your vector, you apply to them a kind of, it's called activation function. I'll talk about that later. Some sigma, and sigma is here component-wise. Component-wise nonlinear function. For example, sigma of t is 0 if t is negative, and t if t is greater or equal to 0. Right. So you have a linear transformation v of x as usual, and then from the output you look at the components, and everything that is negative you set to 0, and everything that is positive, it remains positive. This is, for example, an easy way of coming from a linear function to a nonlinear function. Right? So sigma of this, and so on. So that means that you would that you come up with an optimization problem I want to say I want to minimize. I want to find minimize of the matrices V and W of xi minus Vx sigma and W. Sorry. There was one bracket too much, but so we have here this sigma V of x squared. Right, so this is an optimization problem where you also can find the matrix V and W, but you will see that due to this nonlinearity that you have here, it's not very easy. It cannot be computed in terms of a singular value decomposition, but you have to compute it with different optimization tools in that case. Okay, and it just shows you that, right? I mean, compared to the linear autoencoder, we only have added this very easy component-wise nonlinearity here in the components of the V of x, and that already helps us to receive better results here. And this is what directly leads us to our next chapter, which are feed-forward neural networks. But before I start here, I go to some questions, and after questions we have a short break. Okay, Ryan, are there any questions?
No, everything clear.
I would not say that, right? From no question is not everything clear.
I mean, in the chat box.
Okay, in the chat box. Okay, good. Okay, good. So as I said, we've seen 4 ways of looking onto principal component analysis. One was the geometric approach, where we say so it's a very easy form of reducing the dimensionality, and there are many other machine learning techniques that follow this idea. For example, manifold learning, where you say, well, I'm not going to learn a linear subspace that best fits our data, but perhaps some local manifold structure that best fits our data. Right? This is the generalization into that direction. Then we have looked at the statistical approach, where we say, okay, so this is the data here. We want to find an orthogonal transformation that uncorrelates our data, and then look at the first components that explain most of the variance in the data that we have. So that was the statistical approach. And if we go further in this statistical approach direction, we would somewhat replace uncorrelated by independent. And then we go into independent component analysis, right? ICA, something, I mean, important for me is that you know that all of the directions can be proceeded further and lead to different machine learning algorithms, right? And PCA is somehow the easiest one, and so we can look at it with a different perspective. Okay, so the extension of the statistical approach for PCA would go to independent component analysis. Then we have this noise, this noise model, where we say, okay, if we go for different noise models, like Poisson noise or not Gaussian noise distribution, but another noise distribution, we get another maximum likelihood approach, and we come to another optimization problem that leads us to a different form of PCA that could be, for example, more robust, right? If we say that the noise model is different. So that would lead us to robust PCA. Also a very important direction in looking at signal processing and also machine learning, right? And the fourth one And the fourth one is the nonlinear, is the autoencoders. And the autoencoders approach lead us to what happens in neural networks or in feed-forward neural networks. And in all of these four directions are very important. So you have seen, so I thought it's a good idea if you see them somehow all. Is autoencoder one kind of PCA? Yes, a linear autoencoder is equivalent to PCA. Mm-hmm. This is exactly the answer, Ryan, that you gave. Very good. Okay, good. So then let's have another short break, and then let's go back to feed-forward neural networks and start with that chapter. Thanks. There we go. Okay, feed-forward neural networks. So what are they? And we, if we have a look at unsupervised learning, how we introduced that, or how I introduced that into that lecture. So we have an input X, and if you remember, and unsupervised learning means that we want to find a volume reducing loss function L. Or we have a volume reducing loss function L, and we want to find F out of a predefined function class here, F, that minimizes the expected loss. That was it on a very general setting, right? The example that we just had with this autoencoder is that the function class, right? So the example autoencoder was that F is the class of functions W times V, and W is in R P times K, and V is in R K times P, right? For example. Or for the nonlinear, example that we had, said that F is W times sigma V, and so on, right? So that was the function class here, and we had our loss in that case. The loss was x minus f of x squared, right? Something like that. Okay, good. So unsupervised learning. Then supervised learning, we say, okay, we have an input x and we have an output y. We have a loss function L that measures the deviation of predicted output and true output. And F is out of a predefined function class, again here, F, that minimizes the expected loss. Right? So you always have the same setting. You have a loss function, and you have samples, and you have the expected loss, and then you search a function F out of a predefined function class that minimizes this expected loss. Right? And what feed-forward neural networks are, and as what they can be seen, is a particular class of function. So feed-forward neural networks are a particular function class, and typically they have a lot of parameters to be learned. So huge amount of parameters. This requires a huge amount of training data. And I say something on the general level before I go into the details. The training is computationally very challenging. So you have a lot of parameters that you need to learn, lots of weights in your function f in order to determine the best function f. So it requires a lot of computational resources. But once it is trained, so once the optimal f is found, it has very good properties. So it is a good minimizer for the loss function. And it generalizes also well. So it has very well functions, and this is why the feed-forward neural networks, and in particular these different deep learning approaches, are very famous and led to very good results. Right? It's in the Let's continue. So the idea of this feed-forward neural networks is, as we have just seen in this generalization of the autoencoder, we want to keep it simple but non-linear. Because linear functions, they generalize. I mean, we have the linear functions, and if we want to extend or allow nonlinear functions, we come to a richer class of functions that allows for better approximation. So the idea is we take the composition of linear functions, and linear functions are, I have to introduce a little bit of notation here. Linear functions, let's call them phi of w. They go from some rp to some rm. Some vector h is mapped to some w of h. And we want to compose these linear functions with so-called activation functions. And the activation functions, as I said, are functions that typically act component-wise on a vector. Activation functions that act component-wise on a vector. We have, for example, the rectified linear unit. This was an example that I also just gave. We have the sigma of t is maximum 0 t. Right, that looks like this, as I've just drawn it here. We have more functions, and yeah, many of them are yeah, I mean, the nice thing about this rectified linear unit is it's very simple, it's very easy. Also, if you then come to a later optimization problem, you can handle them very easily, and they lead to very good results. This is the nice thing here. On the other hand, you have other functions like the sigmoid function, sigma of t, which is yes, 1 over, yeah, we already had it here, 1 over 1 plus e to the minus t. That looks like this here, more or less. This is 1/2 here. And there are many more of these simple activation functions. They are motivated a little bit from neuroscience. where you say you need a certain input here, and if this input is above a certain threshold, then this neuron is firing and is giving out information. And so this is somehow a little bit motivated from that. But in practice, as I said, the rectified linear unit has also very good properties and leads to very nice results, although it's not somehow covered by the motivation of neuroscience. To me, it's always a little bit like if you want to fly. I mean, birds can fly very well, but if we want to fly, the engineers are constructing airplanes, and airplanes also fly. So we are somehow inspired by nature, but not copying nature one by one. And this here is also something that, to me, goes in that direction. I have given here this Wikipedia site because if you look at Wikipedia, there's quite a nice overview on different activation functions. Yeah, but for us, the activation function sigma remains abstract. So it's just a kind of almost everywhere differentiable function that acts component-wise on an input vector. And so this is what we do. We keep it simple, but we generalize the function, keep it simple but nonlinear, and compose linear functions with these so-called activation functions. And that leads us to this thing here. So we can have different activation functions. We start with an input x. So this is our input x. And we apply to that input x linear transformation W1 and followed by this multiplication with this matrix W1, we apply this activation function, right? And we end up with this first guy here, and we call it H1 probably. H1 is sigma 1 phi W1 of x, right? And we call that our first layer. Okay, and then we continue and pass this first layer, H1, into our second layer because we apply here W2, linear multiplication with W2, and then we apply the sigma 2, and we end up with our H2 is the same then sigma 2 times H1. Right, that should be it. And this is our second layer, and so on and so forth. Right, until we arrive at some output layer H, I think I call it HO. Okay, and this is somehow a detailed look at what a feed-forward neural net is doing, what the definition of it is. And if you look at that, you see that these non-linearities here are very crucial, right? The sigmas, because without the sigmas, it would just be a concatenation of linear function. And you know that a concatenation of a linear functions is, again, a linear function. So you cannot enrich your class of functions with different layers. You can, so that means with linear functions, you can not achieve anything else than like 2 layers only in practice. Okay, so this is this nonlinearity. So this is X here, input RP, and here output is RO. And of course, I mean, if you look at what we need these functions for, namely they need to fit a loss function, then we also see that the loss function determines also the output of this function f. Right? I mean, the output of this function f has to match the loss function. I see that in some examples. Right? So the definition here is the feed-forward neural nets are a function class, and the function class is determined by what is the so-called hyperparameters, and the hyperparameters are something that you cannot compute by an optimization algorithm, that you have determined somehow differently, is the size of the layers. So which size do we have here in between? This, the size here, and the size, there. Size of the layers, the number of the layers. So how many layers do I want to train? And the activation functions between the layers. All this has to be determined beforehand. And once this is determined, this is the function class you look at. This hierarchy is often, and in practice, it's often very cumbersome and tiring to find out what is the right dimension of your neural net or of your net that you want to find. You have to tune a lot. You have to do lots of experiments, and it's cumbersome. There are some software stacks where you can automatically, I think, look for these hyperparameters. So things are going better in that direction. Engineers provide solutions to that, but there is not a kind of mathematical way of saying this is good or this is not good. In practice, think about 3 to 4 layers that should already work a lot for several tasks. We will have a look at some classification tasks also later. And I wanted to say something to the history of these neural nets, and then I found a link to some blog entry, and Rayyan and Umer put it on the Moodle page, so it's really nice to read. So the early, I mean that's interesting, because saying that these kind of functions are, I mean, you don't have to be a genius to have an idea of approximating functions in that way. So people have, of course, had this idea quite some time ago, and the first ideas of how such a neural network would look like dates back to the, I think, early 1940s already. There were some papers on that, and later on there were some theoretical investigations, but only for layers, for toy examples actually. And the reason why people forgot about these neural networks was that there was just no computational power that allows to train all these parameters, right? I mean, what you have to train, if you plug that into a loss function, is, are these weights. This is what you have to train. And that can be really a lot. Right? We're talking about more than 10 million weights and stuff like that. And so there was simply no computer that could do the job, and you cannot do it by hand either. And so the results were not promising, right? They were rather disappointing. And then it was in the 1980s or so, where Hinton and LeCun started to implement these things and really got some breakthroughs also in practice for practical applications. So from a mathematical point of view, that was not so much interesting anymore, but from a practical point of view, that that was very, very famous. They achieved automatic recognition in the digits for postal codes, and they made that run, and that was really a milestone in this AI and in this feed-forward neural networks. So if you want, have a look at this link. It's really nice. It's a nice read. It would take like 10-15 minutes to read through it, and it's really nice. Okay, so that was it from my side. What we will do next time is we will see how we can train these networks a little bit, at least in theory, meaning that once I have a loss function L, and I have an X, and I have an f of X, right? And I have these Xi's, and I have the mean here of these Xi's. The question is, how can I find the best f out of my neural network function class? Sorry. How can I train that? And that leads us to, yeah. And I will give the answer now, and then we can see how that will look in detail next week. So what we do is we just have a simple gradient descent or a gradient method that minimizes this function here. And if we want to compute the gradient of that function, L, and having this particular form of this f, we can use the chain rule. This chain rule is also known as backpropagation in that setting. And we see how the weights can be updated iteratively in order to learn that function that minimizes this expected loss. Yes, so that's it so far. Stay tuned, and we have a deeper look at the feed-forward neural networks next time. Okay, good.